this is where we left off last time, while debugging the generation of possible moves. There was some issue here, I can't quite remember what it was that we noticed, which might be a good thing. It's been 2 weeks now, so actually 3 weeks, right? Last stream was just nothingness, and the stream before just completely fell flat. So 3 weeks. Well, I can barely remember what happened, so this is gonna be insightful, hopefully. Maybe with a fresh mind we'll figure out what went wrong. I'm pretty sure that something did go wrong, but just not what it was. Alright, so this is where we set the breakpoints, we create the board, render, we generate the tree, and that was wrong. Right, the tree was wrong, not the possible, although the possible moves might have been wrong as well. Not too sure. Alright, so we create the board, 4x4, 1 token each. So that's our board. Let's generate quickly, and it says we have 85. Wait, was it that it generated the wrong moves, or that it generated just wrong values? Which one was it? On the board, how many moves are possible? I mean, on this board, in theory, infinitely many. Not infinitely many different ones, just you could just put everything in a loop, repeat the same 2 moves after a while. Like, for example, blue goes down this left side, red goes up this side. And then they just get promoted and just jump back and forth. So in theory, they could just have infinite many moves. Just that the board state would be finite, of course. 85 different board states. Does that sound reasonable? Look, I'm not gonna try to figure that out. Let's... Actually, let's go back there. Generate map down here. Node state. Value is a node, and node was the score value, yeah, alright. And I think score was, at least with our first attempt, was scoring based on the likelihood of, well, not exactly likelihood, but based on the chances for player 1. And I think it started raining. Dang, I was hoping it would stay dry. Oh well. Yeah, looking at the scores, they don't seem quite right. Score... Can I actually format that in here? I'm not sure I can format it. Let's see if we can. Let's remove that breakpoint for now. Let's go in there. Nope, we can't do this. Was it not D3? Was it N3? So, not allowed format specifier. Okay, honestly, is it using different setup? Like if I go for the standard, yeah, this is valid. D3 D3 not, but N3 would be fine. So why is N3 not available as... What kind of formatting rules does it use? Let me look that up. I'm not sure what to do here. This is something I have to learn now. Okay, so debugger display. Let's see, C# debugger display formatting. So okay, instead of formatting, I should just go for a toString and format that, I guess. toString and string? What the? Then pick N3 in here. Like that, maybe? Well, not quite what I was going for, but... Wait, we don't want to... that method round. Which rounding does it do by default with point? Okay. Smells. Yeah, let's just do method round. Let's see if we can use that. Ease into things, I guess. Score. And let's go for 3 decimals. And let's try that again. I can't use math. Maybe if I go for system, not math. Maybe I need to specify the namespace if it's in that context. Yeah, that did it. Okay, this is a bit better. Let's continue with that. Okay, those values don't seem too bad. Like, we have zeros, where 0 chance of winning. We have ones, where guaranteed win, alright. And we have some values between them, but overall the chances for player 1 are pretty bad. So I guess the entire scoring system is messed up. Let's review how I did the nodes. Again, I have no memory of this. No, I have a vague memory of it. I know I used a tree with one directional links. And I used a dictionary for lookup to see if I duplicate something. Okay, this is here. Wait, let's make a simple example that we can step through here. So generate map goes in here with the initial board, correct. We set up some data. That's the process, initial node. Okay, that's fine. Nodes have the state, the child nodes, and a score. Right. Score starts at -1. Calculation, let's ignore that for now. But it's just a constant. Well, not a constant, it's a value we store. Keep that. Yeah, let's ignore the technical details of how we calculate the score. Just first, is the generation of the tree itself correct otherwise? We have this process, starts with our initial node, just the board. So we have the nodes to process, the stack, and we have our map of nodes. So for each state, we have the corresponding. What do you have? Hash code equals state other. So we did that. So we should be safe with the hash functions or hash map dictionary. C#, sorry, dictionary. That's a process count. We go through the stack for each pop, sure. And then we get the possible moves, which I think we tested for validity, and at least when we developed it, it seemed like it worked. And for each possible state of that node we popped, we try to get the next state that would follow it. And we check if that is a unique state. If that is a unique state, if we did not see the state before, we create a new node using this state. And we push this node so it can be processed, sure, and we add it to the map so it exists from now on. And regardless of it existed or not, we reference it as a child node. So we do have loops in our tree. Any node can reference to any other node in the tree, in theory. So it's not just a tree anymore, it's just a graph, which should look more tree-like. At least in the beginning, the first couple of layers should be a tree, but then towards the leaves, there should be a lot of loops. Well, not a lot of, depends I guess on the settings. But anyway, we have that, and we'll repeat the process. Yeah, so this part looks fine. So the 85 should be correct. 85 possible states that we can get. That seems correct. At least based on how we create it. I have no idea if the data is correct, if these actually are the correct states. I'm just gonna assume they are. I'm not gonna check. So we have our graph with one initial node that starts everything, and then we calculate the score, which is recursive. And we have the processed states here to figure out if we're at a leaf, right? Wait, no, we have child nodes count less than 1. So if we are a leaf, we return this value. If we're not a leaf, if we do have children, we go through here. And if we've never seen this node before, that means we're not looping back to another node, but that doesn't make too much sense because we might still loop back. It's not. I should indicate it a different way. Yeah, so the calculation is kind of nonsense. Well, we knew that. So I guess we're back to just figuring out what the actual method for calculating the good score is. proper score. Right, that's where we got stuck, with the loops. The loops kind of mess up the scoring system. Alright, so things we can say for sure. If there are no more children, if this is definitively the last state we can have, then yeah, we can immediately tell if player 1 or player 2 wins. That makes sense. If we just made the move, so if the next move would be on player 2's turn, and they cannot make the turn because there's no new state we can go to, player 1 wins. And if player 2 can make a turn, or if, oh wait. This is kind of wrong, right? So we take player 2's turn is if this state is player 2's turn. Yeah, okay, no child nodes. There is no next state we can go to, and player 2 is the current player. So player 2 doesn't have any more options for the next turn, so player 1 wins. Yeah, okay, no, that's fair. And any other state is a calculation based on the child nodes, which is problematic because of the loops. I'm not sure if that's supposed to be a spam chat message. So if you could explain why you said that, those 4 words, that would be nice. Otherwise, I'm just gonna assume you're a bot and I'm gonna kick you out. Scoring. Yeah, back to square one. We have definitive scores. How do we calculate the scores when we have child nodes? If I know the child... Okay, if all my child nodes are themselves definitive leaves, then it's easy. If I have no loops... Yeah, but that's not... I can't just avoid them. I have to tackle loops anyway. Let's bring up the drawing board again. Still no explanation for your chat message, so I'm gonna assume you're a bot. Last chance to put anything in to indicate you're not a bot. While I'm getting the drawing board, please go online. Thank you. All right, I'll take that as not a bot. For now. Can never be sure. At least not a simple bot, at least something more advanced, if a bot after all. So curious what's up with that first message. Last stream you also made a similar kinda out there message without any real context, so I would appreciate some explanation. Is it some kind of Twitch meta I'm not familiar with? Let's see, share. Let's go. There we have screen share going. Nice. Let's go back to the drawing. So let's make a tree. Let's say the first ones are straightforward, and then maybe another one down there. And then maybe this one is final state. And let's say this one actually has a follow-up. Could this actually... No, let's go with that. Say this one goes back up there. Song lyrics. What song is that first? The skeletons I would understand, but hilarious, no. Actually, the crazy makes me... Can't think of a... Do I know a song with those words in that order? Can't think of one. Let's say this one is also... No, let's say this one is a definitive down here, and the last one somehow makes it over here as well. Just to complicate things, and this one can go over there. Oh wait, that's not a final state. Wouldn't be fine. Why is... Technology. I'm not sure why it constantly decides to add the screen share. And then how do we end this game? Say this one is pretty much forced into one last round each. So both win here. Well, maybe not a realistic game, but... Or maybe it is, who knows. So these are pretty simple. This would be one. And this is 1, 1. Actually no, then... Let's make them... Let's make 2 like that. This would be 0, 0. What did I do here? What did I do here? What is... Did both just lose? Yeah. Both... Nah, that's... It's actually pretty fair now. 3-3. Oh yeah, not big fan of rap. Yeah, makes sense. Alright, so we have definitive leave nodes, which give us a clear answer who wins, who loses. How do we update the parent score? Like, this is easy. This would also be a 1 then, just child, it's just 1. This one is 1 too as well, because the only score that's available here. This one would be complicated. This would be easy as well. This is still a 0 since there's only leave children. Everything else is complicated. So if we start from the right, now we have this node here, which has 2 guaranteed losses here, and the guaranteed loss over here. The next node. So technically, we know it has to be 0 as well. But can we generalize that? This is an extreme case because all the possible nodes end in the guaranteed value. All the children have a score, let's put it that way. So we can calculate the score from that. Okay, let's just say 0, but a little tick on it. Not too sure about that. This one as well, easy, 0. Because the only direct node after that has a score. Over here, yeah, things get complicated now. So let's say this node here. We get a 0 from here and a no score from here. So only one child has a known score. Can't tell what it is, so we can skip that. This node itself has 1 child, but no score on this child, so we can't tell yet. And this node itself has 1 child that has a definitive score and 1 that loops back, so we don't know the score. And because they are just looping in on itself or themselves, we can never know the actual scores here. And of course that goes up the entire tree here. Same here. 1 child we know the score, 1 we don't, so we don't know the score here, so we don't know the score here. The VODs of the introduction to programming are all online. But that was the first run of the entire series, so it's long and not great. So sure, check it out. Maybe you find something interesting there, but I'm not sure if it's worth it. Not those VODs. Have to redo the series next year. What about... No, that doesn't make sense. This is complicated. How do we deal with loops for proper scoring? Can we... Okay, do we have a way of maybe breaking those loops? To rationalize them away consistently in any and all circumstances. Collapse them somehow? Like, we know that this loop here only has one outcome. It only has one branch it can go to once we leave the loop. So if we know these are all just one continuous loop at most, we could in theory just ignore these. Like, ignore these two and just pretend. Actually, we can ignore this as well then. Drop that and drop that. So we would go from here to there. And this node instead would go also directly there. So we got rid of both loops there. And this one isn't a loop since it goes on a different branch, so that was taken care of. But can we generalize that? I'm afraid I'm just lucky with my example right now. That might be an approach, collapsing the loops to a point where we don't have any loops anymore. Like find all the paths that are looping, and eliminate all the nodes within that loop. Or maybe not eliminating, maybe... Okay, there are potential issues, but let's see if I can do some more. So we have a loop, let's say like that. So the normal path goes down here, but maybe we have a loop up here. Oh wait, that doesn't make any sense. Oh, does it? Can we... I'm not sure about the symmetries in the game. Can we have a state that's identical to a state we had prior, just flipped player assignment? Actually, I don't think that's possible, is it, in checkers? Wait, if we move items across the board, we always have 1, 2, we can jump 2 in one go, but we would delete an item. That's definitely a different state. Okay, we can ignore all moves that would remove a piece from the board, since that would definitely be a new board. That piece is unrecoverable. So we only have to look at moves without deleting an item, which is only one tile further diagonally. Which in theory could be in any direction if we talk about promoted pieces. Can we in that circumstance create a set of moves that would allow us to switch turns? So the same board as far as the pieces go, just with a different player on turn. Let's see, if it's my turn, I have to move a piece from one place to another. And to get it back to that position, it has to be my turn again. Since only I can move my pieces. So to get the exact same position of all the pieces as before, I have to make the move myself. The enemy can't move my piece for me. And that means it will always create the same state of the board, but always for the same player. So no matter what I do, the placement of the pieces will always match exactly one of the two players. It's not possible for the board to just exist in two ways for one player each. In theory, for each placement of the different tokens, you can determine which player's turn it is. Because it's predetermined once you start the game. Alright, so I cannot have a loop that goes from player 1's turn to player 2's turn. It's not possible. Therefore, in my case also, black and white, blue, red tiles can always only point, when they do a loop, to their own color, their own player's turn. Okay, that's important knowledge. I feel like that's very important knowledge. Or maybe I'm just grasping for straws here. Okay, let's just note that down. Nah, not worth the mention. So if it's always tied to specifically ourselves, I mean, the idea would be here to recognize that we have the loop, and the loop has one entry point, or has, in this case, has one entry point and one exit. And so we can just collapse this entire loop and reduce it to just one single tile, one single state. Since the loop can only occur from same color to same color, we can combine these two into one. We don't have to worry about two conflicting colors, turn, players, whatever. So collapsing loops is the way to go. We don't calculate the score. We first reduce the loops. That's it. We calculate all the possibilities, and then we collapse all the loops. And perhaps we can find a way to collapse the loops while we're creating everything. Would that be worth it though? If there are multiple entry points, the same loop might be accessed several times, or a piece inside that loop. If we don't preserve that state, we would have to recalculate everything several times. So, it's trade-off again. Memory versus processing. So a trimming stage where after the generation where we remove the loops. Can we... Okay, let's do a more extreme example. Why is it not? Please delete. That's better. So let's say we have an entry point here and intermediate. Sure. Another. So reduce it to a simple example. And then maybe I have another node here. Goes over here or over there. So maybe put some arrows down. Actually, wait, I made that wrong. Because it's the same playstyle, I can collapse the two, but they would always point to the opposite color again. So that was my mistake earlier. Yeah, I can only point to the opposite color in all circumstances. And if I have a loop back somewhere, it can also only be to the opposite color. That was a mistake earlier. Ooh, good thing I caught it now. I got the right conclusion, I just implemented it, or applied it completely wrong. Oh yeah. And let's go here, and let's say this one can actually go up to that one. This one can go back up there. Or it could go there. That might be interesting. I have a couple of loops, and maybe this one goes out to a completely separate thing. And we have a source for that. There's another source for that. Let's maybe start them off the same way. Doesn't matter for now. So how would we collapse the loops here? Can we do that? Okay, what do we define as loops? A loop would be anything that points to a node in its own path from the root, I guess. So if we go down the way from root, this one is just incoming, so we can ignore it and go down here, and then we have branch in that direction and that direction. And here it's different. Here we can go in that direction, or we can go further down. That can go over there, can go over there. Over here we would... Now that's all just a matter of order right now, in which order I visit those nodes. That's not a reliable... Can I... Like that. Is there a reliable way to define loops? Like, I mean, I can see this is a loop, definitely. And this is a loop. But how can I define that? Generalize it. Detect that. Especially while I'm building this graph. I guess I can't. Not reliably. Now, while I'm building the graph, I can't, because I don't know if there are connections, but once I have the graph, how do I formalize it? Graph theory. God, I haven't worked with that topic in over 10 years. And I wasn't exactly brilliant at it back then, so yay! Okay, first, define loops. Find a way to find the loops reliably. Isolate them. And then find a reliable way to collapse them. So I don't have any loops left. Wait, no, I can't do that either. I mean, I can collapse the loops for calculating the scores, sure. But I can't actually collapse the loops themselves, because if I just collapse an entire piece here, I wouldn't know the scores for these states. So while a computer, a perfect computer, would not use any states in here because it knows that there's no point in it. Unless, of course, that's part of the overall strategy. Normal player can, of course, hit those states in between because it doesn't care, well, the player doesn't care about the loops. Might actually be part of the strategy and they just randomly play. And we end up with a state that's inside the loop that I would remove. If I remove them, the computer doesn't know the state and doesn't know how to calculate that. So we need to leave the loops in. I can't just remove them from the graph. Okay, so I can't collapse the... I can't just do this. Not for... I can do that for evaluating, yes. So with this approach, I can't want it down to this is a 1, this is a 1, it's a 1. And this would be instead be either 0 or 1, so this would be 0.5. And then I can make 0.5 and 0, then so it's a 0.25. That's a 1 to 0.25. What's that? 37.5 plus. Wait, no, what I'm calculating? 375. 5. Oh, 6. 625. Yeah, that makes more sense. Does this reflect the overall game though? I mean, if I just look at the leaf node, the final states, it looks actually like 50-50, so both players have the same chance. But considering that on this branch I have a chance to just immediately go to when... Oh wait, this entire graph was wrong. Right, forgot. Because of the... I can't make those connections, this loop here. I can only have that tied to that directly. So this should actually reflect... If this would point there, then yeah. This is also all wrong, it's all wrong. This entire graph is wrong. But the idea is good. Let's try that on the new graph. Actually, let me turn on the lights here. Just a moment. That's better. Now then. In this graph, evaluating the maybe my mistake is that I'm preemptively creating this loop at all. Because in theory, I mean, that's just not worth it. Because there are eternal loops possible. So if I don't cut them off at some point with my map, it would just have an infinitely deep tree. It would just never end calculating all the possibilities, so... I could make a hybrid system where I attempt to map out the entire tree, but once I recognize a state as a duplicate, I give it a couple of... And that's also just... nah. It's better to have the tree directly use loops. Makes the generation a lot easier. Saves me memory and processing time, and it's overall just way more efficient. Just I have now to do Just have to adapt the scoring system for dealing with the loops. So it's gonna go like actually, what loops are there? We have this loop here. That's definitely one loop. Can just go this route the entire way. Or I can go down here, around that, and then back here. Larger encompassing route for loop. So I got 2 loops, if I see that correctly. But that's just what I figured now. Or figured out now. Thanks, soul brothers. How do I attack these loops properly? How do I... God. Directed edges. Not just a standard graph. Directed edges. And I have a path I walk along those edges. How do I identify all the loops in my graph? I could look that up. I'm pretty sure there are standard algorithms for that. If I'm lucky, they are not even NP problems, which would be great, but I'm not sure if it is or not. There must be a good way to find those, or some generalized method of identifying them or classifying them. I could try to find, okay, one option, I could just try to find the shortest route from the root, which will be a single node, to every leaf. And then anything that's not on any of those shortest routes will be part of a loop, or must be part of a loop. Right? So... Hey, can you please change color? Thank you. So if I go down here, that's 1. And of course the second one is down here, and there's another one down here. And those are... Actually, that's the second shortest route for that one. That is, those are 2 equal routes, equally short. And actually I can also go over here, just branch over. It's also not shortening it. Okay, so all the red parts, red edges are now part of at least one shortest route. I know calculating those is gonna be a pain, but it's doable. That leaves, of course, now 2 edges that are not accounted for, which is interesting. So this one and this one, because they're not part of a shortest route, that means these are a possible path for something, but not the shortest one. Does that automatically mean they are part of a loop, though? In this case, yes. I know they are part of a loop, but can I have a path that's not part of the shortest path? Can I have at least one edge anywhere that's not part of a shortest path from root to any leaf? But that's not looping back on anything? Can I have just 2 different path to a node that are both one-way trips, and one of them being... Yeah, I can absolutely have that. I mean, if I just imagine I have, instead of going from here to there, maybe I'm going from there to here. This would be a longer path, but it's not a loop, so that's not helping either. This is getting complicated. Really complicated. No, I can't formalize it. That could be anywhere, so it's still not... The shortest path doesn't seem to help me. Because I still can't guarantee that any edge I find that's not part of that red part being part of a loop. And I don't care about any edges that are just extending the length of one branch. I care about loops. How do I detect loops reliably? And what's the characteristic of a characteristic? My god. What's the characteristic of a loop? It allows me to go back to an earlier node in my path. So what I should look for is a way to go from... If this edge allows me... If there's a way to go from this node to this node, then... Yeah, I mean, okay, now I guess I have my generalized definition for the loop, which is what I already started with. I can go from the same node to the same node again. Maybe it is that simple. Just take the node and then, I mean, assuming I have a finished graph, I can just iterate through all the nodes within my graph one by one, except for the, well, maybe that's not both. Yeah, go through all the nodes, and then if for each node I check if a child node, one of its child nodes, has itself as a child node, which is an easy check, right? I just go, hey, do any of the child nodes of this one recursively point to this? And then this one has this as a child node, which has this as the child node, then over here, down here, and back there again. So yeah, I can test with an easy, relatively easy recursive test if I am my own ancestor. And then I know that I'm part of a loop. Alright, so I can identify the loops, that's good. Now I need to see what the scoring, if I can, how do I collapse the scoring? Let's try the scoring again. So let's say this one is that. So we have guaranteed loss in here, guaranteed win here, guaranteed loss. That means guaranteed loss, guaranteed win. Ah, things get interesting over here. Both children have different values, but we have 0.5. Plus the average could be either one. This node doesn't have, the child isn't determined yet, so we just take this child. How would we collapse that loop? And this is getting tough. Okay, if we just look at this loop, it would be relatively simple if it wasn't for... I guess it's a good example to figure this out, because that's getting complicated. I mean, that's why I wanted the example, right? Having a more complex setup. Let's see, those are scores. What are my chances of winning here? So if I take that loop and try to figure out what... Alright, let's maybe try to find some interesting parts about this loop. This bigger loop, has entry points. Entry points would be... I don't want to search, please. What's going on? Is it working still? Hello? Okay, it is working. Good. Entry points into the loop would be any edge in that loop that is a child of something else. Okay, everything except for the root is child of something else, but okay. Any node that has a path, a loop node as its child is an entry point. So we have an entry point here. Then that as well as an entry point. And this is an entry point, which is interesting because that's part of the loop as well. And I just realized I should probably switch colors. What do we go with? Let's go gray. So that's an entry point, that's an entry point. This is also an entry point into the loop. No, it's not an entry point into the loop. It's not a node that's outside of the loop that's pointing in. It is itself part of the loop already. So that doesn't count. So this loop has two entry points. Could I maybe just ignore the smaller loop? Wait, can I have two loops that overlap each other instead of being contained by one another? Now, if two loops overlap, that means I can create one larger loop that encompasses both of them. So I can always have one large loop in the end which contains one or more, which contains possibly smaller loops. And every loop that's smaller, that's contained in the larger loop, can be ignored. I guess because it's not effectively changing the behavior of the larger loop. So what I have here would then be going in those two directions, like those to here. Then the 2 entry points into our loop. Oh, this is interesting now. The loop itself. I was going for entry point and exit points and ignore everything in between. Like pretend this loop is basically one giant node. Can't do that though, because we have one entry point here and one entry point technically from up here. So 2 different colors as entry points, and we have 2 different colors for exit points. Can that differ? Right now that's actually a good thing for us. Can we have a situation where a loop has the same color for entry but different colors for exit, or different colors for entry and same color for exit? Could that be possible? Each entry the loop has. Like, if I start with this node just as the first of the loop, or basically this as the entry point, then I could not make this, well, this as well an entry point, unless I point it directly towards this node as well. Instead of having this node here, I would have to point it over there. That didn't quite turn out the way I wanted. And that construct would have equal colors here, but then it doesn't interrupt anything, right? I could just ignore this node then, for example, or keep it. So I can create both versions for the input, that's no problem. Entry into the loop can be done with equal or opposite colors. And I can just extend that indefinitely. What about the exit? Because I can... What is going on? Why is it always closing? Okay, at least it's not closing on stream, but it's closing on my tablet, which is equally annoying. Well, the exit can be... I can put an exit anywhere in the loop. So I can also have equal or different colors. Which gives me interesting problems. So I was thinking first I could just find the loop and then replace the largest loop I find. I ignore all the contained smaller loops, can drop them, and I focus only on the large loops on their own, and then replace the large loop with a virtual node, so to speak, and just find the connections I get from the entry points to the exit points. Though, does that matter? Does it matter actually? If I have this virtual node, so to speak, this non-existent node that's just placeholder for the loop as a whole. That would mean in my case still I'll go down here. That's still a normal node. And then I would have this X node, which can be reached as my placeholder, either through here or there. So my 2 entry points into the loop. And then out of the loop come this one, or this one, which is actually 2 outputs, but I guess I can merge them. Though should probably not. Should treat them as 2 separate things that just happen to point to the same node. I mean, I guess we can trim later on, but doesn't matter. Let's make this a bit nicer. Let's make it a bit nicer. Like that, and this one as well. Alright, so this would be translated into this. For this structure, I can just go loss, change different color now, loss, win, loss, and yeah, this interesting problem again. Now I have different children. Nope, this doesn't help. This doesn't help. I thought I was being clever. I was not. This doesn't help. I mean, I could just pretend this is a virtual node that can do weird stuff outside of the rules, but yeah. This shouldn't be possible. I should not be able to get the node from 2 different colors or get 2 different colors. This virtual node can, which breaks all the rules, and it cannot properly calculate anything. Because right now, if I calculate this like a normal node, then this would be just 1 and 3. So 1/3. And these nodes suddenly had to work with 1/3, which doesn't really reflect the truth. Because in here, it makes a difference. Like for example, from here, this is a 0. What's this? Maybe I need to distinguish. Maybe instead of collapsing that into a virtual node for all nodes equally, I should separate that based on the input node. So if I go for this entry, I would have the tree like that. And I get my virtual node. Or I go over that entry and then have a different virtual node. And these are based on the possible X sets that match. So this entry, I need a different color output. That would be this one. And that's it. So this one only has that one. And this input, the alternative color for the input here, would have this and this. So either, yeah, again, there's 2 different graphs that just merge onto the same there. This one over here, or this one. Okay, and if we go for that, that means we have a 0 here, 1 and a 0. And this is 0, this is a 1, still. Then this would be a 0, 0, and this would be... Actually interesting, we have now 2 paths that go out. Technically we have 3 children now, 2 of them being 1. That means I have 2/3 in here. So 2/3 up here. That means for calculating this, I would actually get 2/3. For this one, sorry, there, I would get still a 0 to 0. So a chance of 1/3 in the end for the root. I can't draw, and I can't write, and I can't believe this is correct. Would this be accurate though? Would this be accurate? So if I just look at the number of outputs down here, then yeah. But that's not actually important, right? So the number of outputs down here don't really matter. They can split off as much as it wants, as long as in the end I have a guarantee over here. The actual leaves don't matter. It's just the input outputs. If this one didn't exist, for example, this branch with this output, I would not be able to make this connection here. So this node would be... This virtual node would be basically like a leaf. There are no valid child nodes anymore. I feel like this is not correct, but it seems correct. So for this, if there's no child node, this is guaranteed. If there are no more child nodes here, I can just ignore this as well. So instead of a virtual thing, I would just go for this directly that. And if I don't have that, I have no more child nodes, this would be the final node then. Which means a guaranteed loss in here, which is correct. And for that... it does kind of reflect the truth. Once I'm inside the loop, I have 2 chances to get out. One over here or one over here, and win. Because it's a loop, it doesn't really matter who started there. So going for this distinction doesn't matter. God, I hate this. Ah. It's hurting my brain. In the best ways. I mean, I'm frustrated and I hate it, but I also love it. Like, this is the kind of brain teaser I really enjoy. Rigging this stuff out, and then feeling completely dumb when I see the solution, quote unquote. If there is a definitive solution. Because you're never the first to find this. I mean, this must be hundreds of years old, this problem, I assume. I mean, just determining the best way to handle the scoring. Like, the scoring itself, min-max, it's a known algorithm. And there must be a way for it to handle loops. So there will be official solutions. And they will be decades old at least, and possibly hundreds of years if it's for some specific scenario. So I can look up actual solutions and compare them to mine. But I want to do that after I come up with my own solution. Because then there's a chance that I actually feel smart because I figured it out myself. Rarely do, but the few times you do, so good. Such a great feeling. Most of the time you just feel dumb though. Because, oh, it's so easy and elegant. And of course some smart people have come up with the best options that I all completely missed and barely understand. Alright. Now with the scoring itself, so if we treat this loop as just one entry point into all three possibilities down here, well, no, three, 1, 2, 3, 4, okay, 4 possibilities. I mean, if we look at it that way, it doesn't matter what happened above, because no matter what I choose here, I'm gonna end up in the loop anyway. So it makes sense that these all don't matter. So maybe I should treat this loop as one singular virtual item that treats everything the same. And then look at the exit points again, which it has 1, 2, 3, 4 children, where one node is the same, but that means I have 50-50 chance, which is actually kind of true. Like, once I'm entering the loop, which I'm forced to, no matter what happens, we will enter the loop. Once we're inside the loop, there are 4 possible ways to exit. And they all have a definitive winner. At least we know the chances from there. Because they all build to their own tree, basically. They all represent the root to their own unique tree with its own score. So my chance is not 1/3. It is actually a unified one loop that has a definitive value of all the children 0, 1, 1, 0. So 0.5 for the entire loop. And so these nodes that enter the loop have 0.5 and the average would be 0.5. So with this tree, I actually have a 50-50 chance of winning. That's the overall chance. Now, how does that work inside the loop? I know my value coming out up here is gonna be 50% for both ends. What's inside the loop? Because during the game, while playing, I will hit these nodes inside the loop, and I need to know what their scores are, because I might know that I have a perfect chance of getting one of the best results here or there. It's exiting again. Why is it exiting again? Go back into the document. Go back into the document. Please go back into the document. Thank you. Like, what are the chances in here? I mean, one way to look at it would be I have one child that's not part of the loop, and I have one child that is part of a loop. And I know the value for the loop. I've calculated that before. So, sorry. Maybe determining the loop and determining the value of the loop is one step. And once I've done that, I can calculate the value inside the loop. Because now I know this will be chance of 1, this will be chance of 0.5. So all the nodes inside the loop have their own value that's not directly equal to the output value up here. And this would be then 0.5 for the loop itself and 1, so 7.5. And then here we have 7.5 down here as a guaranteed score that we also know. And this is a score that we know. So we had 3.375. Yeah, I think. And then we have this one, which is just 0.375. And we have this one, which is 375, or this other loop value, which would be 0.5 again. What's the difference? 2.5, 1.5. 5. I can't calculate anymore. Wait. 0.5 to 375 is difference 1 to 5. After that is 6 to 5. So that's that must be a mistake. Oh, 0, 6 to 5. Oh, sure, that makes more sense. So, 4, 4, 3, 7, 5. Like that. That's not okay. Let's just write it out again. 3, 7, 5. That's better. And those don't measure up to the output values, which is weird. So maybe that's not the way to go. Yeah, that's not how this works. If we ignore the looping, this would be either a guaranteed win down here, or a guaranteed win around here, or a loss. So technically, I would go for 3 possible outcomes, 2 of which I would win. So 2/3. But I have the loop. So I get the values outside the loop, but I don't get the values inside the loop. This is... Okay, if I go for those decisions, would those actually represent the best strategies? If I had this node, actually, what do we have? It's down here. This one has 0.5, 0.0, 0.1. Yeah, has a 0.5 chance. Oh, cool. That works out. 0.5 is still accurate. .5, and then this one only has that one, so it's 0.5. This one has 0.5. This one also. This only has the loop node, so it's a 0.5. This one has the loop node, and the two output nodes, but comes out as 0.5 anyway. So those are 0.5. That's a 0.5. This one is, yeah, the 4375 I had before. So when I'm hitting this state, I only have one choice down here, and then I have guaranteed loss over there and a good chance of winning here. That makes no sense. Then here I have a guaranteed win or a 0.5, so yeah, still go over there. If I'm in this branch, because both are equally valid at this point, go in here. Would one of them be more dangerous? Let's see, that's my turn. This is good because I can determine to stay in the loop, so it's valuable. This one is problematic because the enemy can decide to not go there and instead go there. But I don't want to go there, so that's useless. But that's not my decision. At that point I can't make any changes. I can only go there. Okay, this was an interesting one because I have two different options here. Do they make a difference? If I'm at this node up here, then I get to make the decision which route I go. I can either go down here and possibly loop back, or I can go down there and possibly loop back. If I go down here, the enemy exits the loop directly into the path where I win or I lose. If I go down here, I can exit to a loss, so that's safe, or the enemy can go down to my win down here, and then has a chance to go for win or exit. So technically this is better because the enemy has more chances to make mistakes. Two, in fact. But if I go with my current logic, this would be a 0.5 for the entire loop. So I would go with the 0.5 here. Because it's the better value. But it's not. It's actually the worst decision of the two. Oh, and I thought I had it. I thought I had it. I think the whole collapsing the loop into one virtual node and just treating that as one value is still useful, but only for the nodes outside of the loop. The problem is once I'm inside the loop, I can't just treat it as a new tree anymore because it's looping in of itself. I don't have a definitive route anymore. I lose that advantage. Maybe you should treat them separate after all. Like if we just look at this output down here, I have one exit here for guaranteed win, and later on it's like I go from here, I have a guaranteed win here. Or I go further down to another chance of guaranteed. So this node would be that node, or loss. And I can repeat that. So in this case, this would be win, loss, a win. It's a win, that's a win. That's 0.5, 0.5. So overall that would be 0.75. And I should definitely go that route, which means I should definitely go that route on here. Yeah. Which means this node is right now the one that's bothering me. This is an issue. I can't just evaluate the nodes inside the loop with the loop value. Actually, that means I can also not use the loop value for the inputs. Right now, that's irrelevant. Because the better decision would be on this branch, and in here I'm forced to use it. Over here I can use it, so it's safe, but in theory I might have... For example, if this one had an option to go in here into the loop. Then it would be safer for me to make this decision first, so I can force my way down this side of the loop. Ah, this is getting out of hand. Maybe I should just look it up. I'm never gonna make any progress on this, am I? No, I'm sticking with it. I have to learn this. I have to learn this. And the best way to learn it is to just do it. Without having done it myself, the solutions I find will make a lot less sense. It's better to know it myself. To understand the problem, understand the various angles. I have no smart ideas. I do not know how to proceed here. I'm going through a couple of options in my head and none of them work out if I just go through it step by step, try to evaluate what the outcome would be. Gosh, these loops are actually really... that also doesn't work. Wow, this is... I can't simplify it to this is a loop value. This loop is one virtual node and it has a specific value. Can't do that. That's too simplified. And especially doesn't work inside the loop anymore. How would I probably express this? What? Okay, let's maybe go back. What is the score supposed to represent? The encode should be that if I follow the path with the highest score at each intersection, whenever I have an option between two different paths, or at least two or more different paths, different moves, if I pick the one with the highest score, I should have overall the highest chance of winning. And ideally, if I'm the right player that starts, or if the right player starts, that might be me, that might be my opponent, I should have at least one path with a guaranteed victory. It's a solved game, so there's always at least one path that is guaranteed to win. Just not necessarily my path, it might be the path for my opponent. It just inherently solved games. You have one of the two players will have the guaranteed win strategy. Can't avoid it. Can only hope for that game it's you that gets the perfect strategy. The other player usually has a near perfect strategy that still relies on the opponent making at least one mistake. And even then it's not a guarantee. That one mistake might not be enough. And yeah. So for this, even with the loops, well, it could of course be that this is just the graph for a game where player 1 doesn't have a guaranteed strategy and player 2 does. Yeah, I think that player 2 has the win strategy. So if we assume this one doesn't exist, we enter the loop on either side down here. Either the enemy, player 1 will just immediately tap out in here, or we get the chance to pass on down here into the branch, where we get the chance to just immediately win. Yeah, player 1 has the win strategy. The player 2 has the guaranteed win in this graph. So if we look at it from player 1's perspective, no branch I select should be guaranteed win. But for player 2, there should exist. So in other words, from now, in other words, for me as first player, for which we evaluate the scores right now, which is just the inverse of the opponent's scores, the path with the lowest scores should probably lead down here. Because at least as far as I can tell, that's the winning branch. Like this route down here. That's a guaranteed win for me. So that should have the lower scores for player 1. And these two sides don't really matter. Though in theory this has a higher chance to lose because this should have a higher value. This side should actually have a higher value for player 2 than this one. So this should have a lower score. This loop cannot have the same value for both. The difference between these two nodes has to be reflected here. This has to have a higher value for player 1 than this one. You know, I can't think of a good solution. I think I'm gonna end it here. Maybe next time. And don't worry, if I can't find a solution next time, I'll just look something up. Because I have no intention of just sitting in front of the whiteboard for the next X weeks. So, yeah, with that, thanks for joining in. Have a lovely Sunday. Bye bye.